Hello, everybody. In today's discussion, we will connect things that we have already learned, that's covariant derivative, and geodesic, which came out to be the shortest distance between 2 points. That's what we defined as geodesic. But we'll define it in a little different way today and connect the covariant derivative with the geodesic through the notion of parallel transport. But before that, we'll also revise our understanding of the analysis of vectors and scalars and tensors such that everything falls into place properly. So let us start. Let's ask the question first that what is a scalar? A scalar is can be considered as a tensor of this type, 0, 0 type, and you know that a tensor of type Mn has d to the power m plus n components in d dimension. So this has d to the power 0, that is equals 1 component. Now when I call a scalar, so the d is the dimensionality. So that every time we will talk about, our dimensionality will be either d or sometimes d will be equals to 4 because that's what we deal with. Our space time is 4-dimensional. Now you see, this is only one component, but when I talk about it, so it can be only one component, and that component is fixed everywhere irrespective of the space time. So I can have the scalar, let's call this scalar psi. So let's call this psi. Same in all values of the coordinate. That's all coordinate points. So this is one example. So this is, because it's example, I put it with this star. So this is one example that I can have this scalar, which I call the scalar, which is only one component. Now it becomes only one number. The number is same everywhere in the coordinate. Okay. So this is the speed of light is such an example. Irrespective of where you are measuring it, in any reference frame, the value is always the same. But I can also have a different type of thing, which now I call the scalar field. So what is a scalar field? It is one function, and let us denote the scalar field as phi. So it's one function phi of the coordinates. That is, it maps, so if phi maps the coordinates into a number. So every point in the coordinate, I have a value of phi. Everywhere in the manifold, the function has one value, but it can be different at different points in the manifold. The value can be different at different points in the manifold. That's why I call it a function, not a single number. Okay. Now, as we have seen, so let's ask the following question now. Okay, so I have the value of this function is different at different points in the manifold. But what if I ask the question that given a coordinate system, how these values will change? So if I change from one coordinate system x alpha to another coordinate system, say x beta prime, what will happen? So the question is, what happens to phi in a coordinate transformation? Okay. So what will happen to phi in a coordinate transformation is the following. So you have phi. Now this phi in, say, the x alpha coordinate systems is calculated at x alpha, and you calculate it in the same manifold obviously, but in a different coordinate system. These two has to be same. That is why we call it a scalar. And this property is called the invariance. Remember that here x beta prime transfers in the following way. So what you have to do is you have to put in the values of the coordinates of the same point. Phi is calculated at one point in the manifold. That point has certain coordinate components x alpha in one coordinate system. It has certain other coordinates components x beta prime in some other coordinate system. If I calculate the value of phi in both the coordinate system for the same point in the manifold, they should be the same. The value should be the same. And this is what is required also for phi to be a tensor of rank 0. Why is it so? Well, remember that rank 0 tensor has only one component. Now, we also know that the components of a tensor in one reference frame is given by the linear combination of the components of the same tensor in other reference frames. Now, because it has only one component, one way you can have the linear combination is making it the same. So that's why it happens. So that's a scalar. Now let's come to a vector. So for a vector, so let's talk about the vectors now. So these are tensors of type 1, 0. They're members of a vector field. Sorry, vector space. Because it's a tensor of rank 1, this will have d components. In d-dimensional space, of course. Now, it is possible that such a vector has the same value in the entire manifold. So can have the same value in the entire manifold. So irrespective of the position or the point in the manifold, it has the same value. Just like we talked about, the scalar c, the speed of light, has the same value everywhere in the manifold. What is the example of such case? Well, if I consider the velocity of different, so I have two low range frames, and I ask the question, what is the velocity of the observers in the other low range frame to the observers in one frame? And irrespective of where those observers are, all the observers have the same relative velocity with all the other observers in the other low range frame. So that velocity is a vector. The relative velocity between the two frames is a vector which doesn't depend on where you are. So that's a case where it has the same value everywhere. On the other hand, if I have a vector field, now the components of the vector will have different values at different positions in the manifold. So this is the case where the components of the vector have different values at different points in the manifold. So if I want to define a vector field, what I need to do is that I need to define d functions, and the functions are like, if I call those a alpha, alpha stands for the which vector field that you want to define, which component you want to define. So there can be d values of alpha. Alpha equals alpha goes 0, 1, 2, 3 for the case of general relativity or special relativity. So these are functions of the coordinate. Each of them are functions of the coordinate. And now if I do a coordinate transformation, so then we have seen that they have certain transformation properties. So what are the transformation properties? Well, what we are doing here is we are asking for the same the same vector at the same point in the manifold, and if that same point in a different coordinate system is the different coordinate system here I denote by the prime here, so alpha prime, this obviously now it will be function of this say x mu prime. This will be related to a alphas in the following way. Okay, so it's the coordinates of one reference frame, this is the coordinates of the other reference frame, the values of the vectors or the functions as a function of that reference frame, and this function is of a different reference frame. And you see that these functions are linear combination of the functions in the other reference frame. Okay, this is what the way the vector will transform. Now, we just talked about vectors here. We can talk about one forms as well. One forms will almost have the same structure, but remember that there are few things here. The one forms will be a vector of type 0, 1 instead of 1, 0. They will also be member of vector space, but the vector space of one form is different than the vector space of vectors. I cannot do an operation of one form and vector together. Like I cannot define a dot product between a one form and a vector unless I define a metric and bring the one form, map it to a vector, and then define the dot product between two vectors. That is possible, but one form and vector, I cannot directly define a dot product. But the one forms will also have one form fields, and they will have transformation properties, which requires the inverse transformation matrix, if you remember. Okay. So the same pattern also, if I now go to the tensors also of higher ranks, the same pattern will continue. So we'll not, we have discussed those in length, so we'll not go into that. Now, let us come to the following concept, which again we have already discussed, but let's come to the concept of a curve. And we are basically talking about a parameterized curve. But to be very frank, a curve is always something which is parameterized. So there is if I call it a curve, it's a parameterized curve anyway, but just wanted to emphasize this. So what is such a curve? Well, we have a parameter, say we have a parameter lambda. So lambda can be a member from the real line, essentially. It's real numbers, which defines the curve in the following way. We say that the curve is D maps or R D maps. D means the D number of maps or D number of functions that gives 4 coordinates for each lambda. So that gives not 4 coordinates because we are talking all about D. So this should be D coordinates, but the example we will of course write only for 4. I will get this number x0 by the map x0 on the parameter lambda. The same parameter lambda will also give me the number x1 by the map x1, map or function. I'm using them synonymously here. Okay, so for each lambda, there are these 4 values, and that defines a curve that we have seen already. That defines a curve. Remember that if lambda, the parameter itself, is if we are talking about a trajectory and the parameter is the proper time spent in the trajectory, so then these are the coordinates of the trajectory. Now, so this is a curve. Now let's say that we have a scalar field, phi scalar field, which is, remember, is a function of all these coordinates. So this is defined, the values, once I have this map, the values of phi are defined in all points in the manifold, right? So we want to ask the question that how phi changes along the curve C. Change of phi along the curve. How will I write this? Well, this change of phi along the curve is parameterized by lambda, so it's essentially d lambda. And you see, phi is explicit function of x. So I should take the partial derivative of phi with respect to the x's, and then x are function of lambda. So that is defining the curve. So this is essentially this. Or sometimes you, if you wish, you can write this as del x alpha del lambda del x alpha. This entire thing operating on phi, and this we call a directional derivative. Why do we call it a directional derivative? Where is the name direction coming from? Well, you see that if I have a curve, del x alpha del lambda essentially gives me the direction of the tangent vector of the curve, or it gives me the tangent vector of the curve at that point. And what all we are doing, we are taking the derivative at the direction of the tangent vector, because you see that that's what is being done here. Can be written in terms of a dot product, though it is not written in the same way. If I have a metric, it can be written in terms of a dot product. Okay, so that's why I call it a directional derivative. This I can write as, if I call the directional derivative to be w, so this I can write w alpha and then phi comma alpha from our old notation. So this is a vector and this is a one form. Or these are components of vectors and one form. Now, if we look at this object, one form, this obviously have this type of tensor structure. So it's a 0, 1 tensor, right? We will write this as gradient of phi. So this is the change of a scalar field with the coordinates. Okay, so let us look at these a little bit more closely. See, what have we done? So we said that we have a scalar field defined in the manifold. So every point, so there is a function which gives me a number for every point in the manifold. And this number doesn't change for that given point, even if you change the coordinate system. There's only one number associated with each point. If I now define a curve in the manifold, and if I ask the question that how my phi changes along that curve, then that turns out to be a contraction, which I have written here, of the tangent vector of that curve at a given point and a one form. And that one form is nothing but how this phi changes as a function of the coordinates. Okay, so that is how we defined the gradient of alpha, which is the change of phi as a function of the coordinate. Now let's ask the question, well, this is, we have defined for a tensor of rank 0, a scalar. So the derivative of that with respect to the coordinate gave me a one form. So the, if you wish, the covariant, the lower index, has increased by 1. What if I do the same thing for a vector? So how does a vector changes? With the coordinates? Well, I'm saying with the coordinates, you can imagine that it should be defined for any coordinates, but it's essentially how the vector changes as you go from one point to the other in the manifold. And now we are not moving along a curve for the time being. We are going from any point to any other point, nearby point in the manifold. Okay, so say the vector component vector is A and the components are A alpha in any coordinate system, and then we are asking what is this quantity, and say this quantity, I let us write this as R alpha beta. We do not know, this may not be a tensor. We do not know whether it's a tensor for the time being, but what type of component it is? So it has d to the 2 uh, components or functions. So these are d to the 2 numbers, or let's not write components, I should write d to the 2 functions. Plus, just like the vector was one function or 4 functions, or d functions, not one function, d functions, here it is d squared functions, because this function can be different because you took one particular component of the vector and then the change of that in one particular direction of the coordinate. Okay, so let's ask the question, how will this thing transfer? So we like to figure out what will be our mu prime in terms of our alpha beta. How do I do that? Well, first I start with, so r mu prime b prime is nothing but del a mu prime del x nu prime. All right. Now, del x nu prime I can write in terms of the derivatives with respect to the previous coordinate, the before you do the transformation. So this let's say this is del alpha, and then I have to do, this is the chain rule or Leibniz rule, whatever you say. So it is, I'm just doing that. So this is this. Why did I do it? Because I want to also transfer a mu prime to its unprimed system, and that transformation law we already know. So this is something like this, right? So let's write that down. And then del x alpha. Okay, so what do I get? I get that del a mu prime del x nu prime, which we wrote as r mu prime nu prime, this is equals to, so I will have a term here which is del a beta del x alpha, and with that I will have this is how exactly, if R is a tensor, how exactly this is supposed to transfer, because this is just R alpha beta or R beta alpha. But then I have this extra term which is unlike a tensor. So this term makes sure that it is actually not a tensor. Okay. Now, why does it come in? Why does this second term comes in? It comes in because in this case of transformation, as we have seen already, that the basis vector changes, right? As the basis vector changes, when we do the transformation from one point to the other point, I cannot only take the derivative of the amplitude of the vector, I have to also take the derivative of the basis vectors. Now, this only happens when the transformation is coordinate dependent. We have seen one example from Cartesian to the polar where the transformation was coordinate dependent. If the transformation is coordinate dependent, then remember that transformation, so let's say transformation matrix. So what is a transformation matrix? In this particular case, I can write it as say x, just writing one of them. It looks like this, right? Or if it's of the one form, it's just the inverse of this. Now, if this is independent of which point, it's independent of the coordinate essentially, then the second term will be 0 because the second term has the the derivative of this. If the transformation matrix is depends on the coordinate, then this is non-zero. This now we can see explicitly when this is 0 and when this is non-zero. Okay, and when the transformation matrix depends on the coordinate, then you know that your unit vectors will change, so everything is consistent. So this r mu nu or r alpha beta is not a tensor. So doing a derivative of a vector, we do not get a tensor. So that is where we defined a covariant derivative. So this we defined a covariant derivative. This is definition, so you cannot ask why it is defined so. But there will be some logic. So first of all, that we will write it just like before. We'll write it like this, or sometimes with a semicolon alpha. This, remember that for the derivative of the scalar, it change a scalar which is 0 0 tensor to one form which is 0 1. So here also we will expect that it changes a mn tensor to a form which is say mn plus 1. This is how we will construct it. Then it has to be a tensor. The covariant derivative itself will be a tensor. We want this because we want to write things in terms of tensor equations. As we have seen, the equations form doesn't change if you go to different reference frames, and that is what we'll need to construct a mathematical theory around the principle of strong equivalence or Einstein principle of equivalence. So I want the covariant derivative. I want to define a derivative of a vector with respect to coordinates, which the derivative itself will be a tensor. So it's a tensor, so it will be linear in its components. So linear or affine. Sometimes it's also called affine derivative because of that. It should follow rules of derivatives, so follow chain rule or Lemdrich rules. Okay, and so it should respect the scalar case. So what we have already defined for the scalar derivative, it should also have that. So let's just write these. So what is meant by linear is the following: that if I have the covariant derivative operating on a plus b, so a and b are two vectors. Now this is okay. So that though we have said that's the covariant derivative of vectors, but it can generalize it to any tensors. But let's do it with vectors for the time being. And the Leibniz rule or the chain rule is essentially that this equals okay. So I leave it for you as homework to verify that these are true using the connections, using the Christoffel symbol and derivative of the covariant definition of the covariant derivative that we have already gone through. Okay, so now let's see that what can we do with all these definitions. We introduced a derivative of a scalar in order to see how it changes along a curve, and then from that, while seeing the change of the derivative or change of the scalar along a curve with respect to the parameter, we found that we need to define something which is the derivative of the scalar itself as you go from one coordinate to the other. Now, in physics, we want to see how the vectors changes. Physical laws are written in terms of differential equations. Equations of vectors or tensors in general. Right? So we want to see how a vector or a tensor changes in when doing physics. So one example is that the velocity of a particle in force-free environment or force-free condition. So how does it change? It doesn't change. So that's Newton's uh, first law, or rather second law if you wish. So that's where we compare vectors as it moves along a curve, right? We can also ask the question that how the Maxwell field tensor, which is a second rank tensor, changes along a trajectory. So see, where do we need this? If I want to calculate the force on a particle along a trajectory, I need to know how the Maxwell field tensor is there at different points in the trajectory. So in physics, we ask this question. So it is important for us for a general manifold, to define these changes, and that's what we have done in terms of covariant derivatives. Now, in gravity, we have seen that we don't have a global inertial frame. General or gravity doesn't allow a global inertial frame. This we have seen a couple of lectures back. But in neighborhood of any point, in neighborhood of any point in a manifold, which defines the global frame, we can we do get a inertial frame. That's the freely falling, the frame defined by the freely falling observer there. This is a local inertial frame, of course. Right. So what I need to know is to compare measurements of things like velocities or the Maxwell tensors we need to see, or we need to transfer from one local inertial frame to the other. So what we are saying here, imagine that you are in a gravitational field, and in that gravitational field there are two different freely falling observers who has their own inertial frames, local inertial frames, and they perform certain experiment. And the strong principle equivalence says that these experiments should be able to be written, the results should be able to be written in a differential equation. And that differential equation form of that should not change if you go from the one to the other. Which essentially means that, say, so one such differential equation can be the fact that there is no force acting on a particle who is moving and supposed to move without changing its velocity. So which means now I have to compare the velocity of this particle from one freely falling observer's local inertial frame with the local inertial frame from the other freely falling observer. Question is how to do that. So we need to figure out a way of comparing tensors at two different reference frames. And we'll start with a vector, we'll demonstrate with a vector, but the same thing applies for tensor as well. But let's start with a vector, and then we are bringing in the notion of parallel transport here. So what is parallel transport? Well, if I am living in a two-dimensional world, if I'm living in a flat world, just like the surface of this board, then say I have a line here, and I have a vector which I want to move, which I want to compare the value of the vector at the point A with the value of the vector at point B, or maybe the point B has a different vector. I want to compare the vector at point A with the vector at point B. Well, in this board, there is no problem in doing that because, say, the vector is here, is this, and I can take the components. Uh, the unit vectors are global, so the unit vectors are same in both A and B. So let's call this E1 and E2. So these are the unit vectors. So if I take that vector, let's call that vector P, I have no problem in comparing with that vector and the vector R here, say. But in principle, what I should do is I should move the vector P towards the vector R. So virtually, and then compare them. And you can see that they might have a little different direction and uh, almost same amplitude. Okay, this works quite well in such a plane of the board. But imagine that I am doing the same exercise on the surface of a sphere. Okay, now the surface of a sphere, so this is on a plane. The surface of a sphere is not possible to be drawn here, so what I do is what is called a perspective drawing. And this is one of the hemispheres I'm trying to draw here. Okay, so that gives you some idea about our brain tricks ourselves to have see this as kind of three-dimensional object. All right. Now, if I have a vector here which is looking in this direction, and let's use this color with the vector. So this is the vector now. This is the vector P at the point A, and say this is the point B, And now there is a vector r here. The question that you ask is, how do I compare p with r? The unit vectors at p, let us draw the unit vectors at p, and this is here. As you can see, we are dealing with the coordinates, the polar coordinates. So this is E1 and this is E2. Unit vectors at p, if I draw, this is E2 prime and the E1 prime should be radially outwards. And you see, it's very difficult to compare such two vectors. Okay. So how do you compare the vector between 2 points? Is that you transport this vector parallel to itself. Always when you transport it a little bit along that curve, so transport it parallel to itself and bring it to the point P. So transport the vector along curve AB always keeping it parallel to itself. Okay. The question is, how do I do this? How do I know that the vector is staying parallel to itself? Now the curve is defined by a parameter lambda. So let's say that the curve is defined by a parameter lambda. Okay, so the curve is defined by the parameter lambda. If I consider dx alpha d lambda, this is the tangent to the curve at any point. Now we say that the vector is parallelly transported so that if the vector is parallelly transported, the vector is A, say, then this is how I parallelly transport the vector dx alpha d lambda gradient, which is again respect to lambda of a some component, should be 0. What does it mean? It means that the type of the whatever derivative of this is, which we will say a little shortly, the derivative of this vector along the direction of the curve is 0. So along the direction of the curve, I have not changed the derivative of the components of the vector, then I will say that it is parallelly transported. That quite makes sense here, because that's how I am transporting the vector. If there is a component of the vector here along the curve, which is this much, I'm never changing that as I am moving it parallel to itself. So that is what you are doing also here. right? And this derivative is nothing but the covariant derivative. So if I write this dx alpha d lambda, I write this in writing down the covariant derivative explicitly is del a mu del x alpha, and then I will need the Christoffel symbols, which now, because we call this as an affine derivative, we call the covariant derivative as an affine or linear derivative. Affine means linear. So this is sometimes called the affine connection. Sorry. So it is this, which is equals to 0. And if you write it more explicitly, see the first term is essentially del a mu, or it's not del, but d mu d lambda, if you use the chain rule of differentiation. And the second term is mu alpha beta a beta dx alpha d lambda equals 0. So if I have a curve along which I want to translate a vector parallelly, then I have to make sure that this equation is valid, essentially. That's what I call a parallel transport. Now, you see, in case of the Minkowski space, or even if you come down to the 3D Euclidean space, where all these gammas are 0, the parallel transport essentially means that along the parameter, as you change the parameter, the components of the vector doesn't change, because that is the d mu d lambda equals to 0. Okay, but once you come to the more complicated manifold, the general manifold, you have to carry over that term with a Christoffel symbol, or which we also call the affine connection. So let me just okay. And what you have got out of doing this is a tensor of rank 1, 0. So this is the tensor equation of rank 1, 0. So again, it's a tensor equation, which is good because if it's true in one reference frame, it should be true in all reference frames. Now, given this, let's go one step further. What we have done here up to here is that we have defined how we can translate a vector parallel to itself. Now let us ask the question that what if we translate the tangent vector of a curve along the curve parallel to itself? So if we translate the tangent vector of a curve parallel to itself, and calculate the directional derivative, along the curve of its tangent vector for a special type of curves which we call geodesics. This derivative is 0. Okay, so what was the directional derivative? So let's go back. So this is the directional derivative in this case. We defined it earlier. In case of the scalar, remember that this was the directional derivative for a scalar, and here del x alpha for a vector has to be replaced by the covariant derivative. So this is the directional derivative here. And this is where we are defining geodesic. Geodesic curve is a little different than geodesic, but we will not go into that. So we are directly defining geodesic here. So how will it be? Well, all that I have to do is that in place of mu here, I have to write the tangent vector itself. So the covariant derivative of the tangent vector itself is this equals 0. Or I can, let's keep it here like this. Okay. So this is the expression for geodesic. But last time we said geodesic to be something different. We said that it's the shortest distance between 2 points. Okay. Now, how does these two are the same? Are they same, or we are defining geodesic every day with a different definitions? Okay. So let's look at the physics part of it, which will make us the connection, which will let us make the connection between these two geodesics. So let's go back to Newton's first law. What does it say? No force applied. This is all happening in inertial reference frames. Particles moves in straight lines. Straight lines means shortest distance between 2 points. That is the definition of a straight line. Now that is what we derived last time, and we found that the equation for shortest distance between 2 points is given by, if u is the velocity of a particle, then the particle will follow a trajectory which is given by this. This is, or the equation for the world line of the particle, if you want to be more precise, is this. This is what the Newton's kind of Newton's first law gave us. Okay, and now this is not happening in an inertial reference frame. This is happening in any manifold, and that's the quantum leap, or that's not the quantum leap, but that's the uh, gravitational leap that you have taken already. What does Newton's second law tells you? No force, velocity remains constant. Right? Velocity of a particle remains constant along the trajectory. What does it mean? It means now if I consider this parameter lambda here as the proper time which parameterizes a trajectory, then this expression is essentially telling us that the velocity is telling us this rate of change of velocity, which is du, say du mu, d tau. See, if lambda is tau, then dx mu d tau is u mu, which is the for velocity, and you are taking derivative of that with respect to lambda again, with respect to tau again, and you will see that this will again boil down to which is what we called the expression for geodesic, and it's exactly the same as what we had here. So that's the connection, that the variational principle, which extremizes the distance between two trajectories, gives you the same geodesic as you get as the curve along which the covariant derivative or directional covariant derivative of the 4 vector doesn't change. So we'll carry forward from here now. We'll see what more a parallel transport tells us about the manifold in which the parallel transport is happening. And as you can see here in this, both of these expressions written here are exactly the same expression, but these expressions are now not bound in inertial reference frames. These are written in any reference frames. These are true for any manifolds. These expressions you have actually used when you talked about motions in configuration space. So this is nothing new. This is not attached to general relativity only. Motion of a particle in a constrained configuration space is also described by exactly same equations. And we'll see but what extra that we get out of the parallel transport in the next lecture. Thank you. That's it for today.